Hello, everybody. I am Ismail Benayed, and I'm happy to participate in this virtual summer school on deep learning for medical imaging. I hope that you're enjoying this virtual version so far, and hopefully the next time it will be in person. So today I'll be talking a little bit about weak supervision. So this talk will be divided into two parts. The first half, it will be me discussing some aspects related to mostly regularization for weakly supervised learning, of course, with focus on medical imaging application. And the second part will be discussed by Jose Dolz. So the subjects attract wide interest, not only in medical imaging, but in the general area of machine learning, computer vision. So why weak supervision is important, specifically for medical imaging? So perhaps I wouldn't be telling you new information when we say that deep networks and specifically convolutional neural networks are quite dominating computer vision and also medical image analysis. And while, during this part or during this talk, we will be focusing on maybe one specific running application, which is segmentation, but the concepts are basically general. And are basically, used in the general area of weakly supervised learning. So one of the important aspects in recognition is semantic segmentation, which is basically here you have an example of natural image. And the task is essentially to try to assign automatically a meaning to each pixel in the image in the context of natural images. For example, here it's an autonomous driving scene where you basically want to give a label to each pixel, for example, tree or street, and so on and so forth. And of course, maybe by now you would have seen a lot of maybe examples in medical image segmentation. Probably medical image segmentation is the main subject today in medical image analysis. You would probably see half of the paper or more in the main medical imaging conferences like MICCAI focusing on this problem. And it's essentially semantic segmentation, but the semantic classes are not trees or cars, but are brain structure. For example, here are some examples of semantic segmentations from our team, but these are just small fractions of the problem that are of high interest clinically. Essentially, if you succeed into having very good segmentation algorithms for medical imaging, then applications, very important applications, will follow, from disease diagnosis to planning treatment, for example, organ at risks for cancer, or also subcortical structures of the brain, or vascular structures, or brain tissues, or tumors, and so on and so forth. Applications range from, for instance, planning treatment to disease diagnosis to follow-up, and so on and so forth, because from this segmentation, you would extract measures that are valuable clinically. And it go even beyond patient treatment and disease diagnosis to even understanding complex diseases like Alzheimer's, so to even pushing the boundary of health-related research. So I think I'm not going to dwell a lot on the motivations, but essentially what I'm saying here, this segmentation will be the running example of discussing the interests and some interesting methods in weakly supervised learning. It will be discussed in the context of segmentation. So this is just some simple examples that shows you why the problem is interesting. So what you see here on the left-hand side is essentially an example of semantic segmentation of a natural image, where we know that we can reach excellent performances. Basically, in the last years, we had huge developments with deep networks, but those performances are typically attained with full supervision. That is, for each image, you would have to have a label for each pixel, probably for a few thousand of images, so that you could reach a good performance. And typical data sets like for natural images like Cityscape, for instance, you might need up to 1 hour or 1.5 hours for a human to manually label those images. And it might even go to several hours for a medical image. On the right-hand side, what you see here is an example of weak supervision, where your training data is not what you would see here, a pixel level labeling, but actually just a high level labeling of the image. For example, I just know that the image contains a person and a horse. Okay, so the labeling here, we call it image level tag. For example, it's a form of weak supervision for segmentation. But of course, during prediction, I would be asking my algorithm to predict pixel level classes. So my training is limited, is weak, but my prediction is full. So this is an example of weak supervision in the specific context of image segmentation. This is another specific example where essentially the idea is very simple. Either you have weak annotations that are not complete, or you have also partial, where just a fraction of your data is labeled and the rest is not labeled. This is a very typical example where your labels just are a few, let's say 1% of your pixels in your training data are labeled, like what you see here, for example, in the form of scribbles. And this is a specific setting of what we call semi-supervision. So semi-supervision essentially is basically have a few data points that are labeled, and the rest of your data is not labeled. Okay, so this is by definition what is a semi-supervised learning setting. So of course you can have a lot of settings from weak supervisions like image level classes or semi-supervision like scribbles, points, or bounding boxes also is a form of weak supervision. So there are different ways of supervising segmentation in a weak or a semi-supervised way. And there's probably, this is just a small fraction of papers that on the subject. Here I made a few choices from medical imaging and computer vision, but the literature basically abounds of methods that try to tackle this problem, and this gives you an idea about the importance of the problem. So full annotation are problematic. They are problematic even in natural images, even though we have data sets here that have thousands of images, even for the problem of semantic segmentation, so thousands of images that are labeled pixel by pixel. If we look at medical imaging, we are not anywhere close to, for example, the 10,000 pixel level labeled images of Pascal VOC or the 5K of Cityscape, which are common public data sets. And the reasons are clear, basically. First of all, you cannot have everybody label medical images. You cannot do crowdsourcing. Everybody could label maybe or recognize a horse in a natural image, but this is not the case in medical images. So you cannot do something like this and ask everybody to label images. If I show you this type of images and you're not a medical doctor, you have no clue about what does the image depict. And so you need expertise, and also you would need also maybe several hours of annotations of radiologist time. So this is one aspect of it, okay? But it goes more than, let's say, we could probably try to get annotations from experts to a certain level. But this is not the full story. This is not the full difficulty of it. There is also what we call domain shifts. Let's say you trained your data on some MRI in some clinical sites for segmentation of prostate or brain or lung images and so on and so forth. And then you go to a new clinical site. And then the acquisition protocols are different. The MRI protocols are different. Or you even go to another modality. So this is what we call domain shift. If you imagine that your images lie in some two-dimensional space like this, the image appearances, the characteristic of the regions of segmentations that you try to predict might change due to changes in the population, due to changes in the acquisition protocol, and so on and so forth. And as a result, they do not lie pretty much on the same clusters or manifolds. If you think of images as 2D points in some two-dimensional space. So this is what we call domain shifts. Let's say your training data is on this source data, like the blue points, and then you try to do predictions on this target data, the red points. So what you would expect to see is a significant drop in performance. And this is a serious challenge, right? Because we could not, we could not try to annotate data in every single possible scenario of image acquisition or of population and so on and so forth. So generalization to unseen data that is significantly different from the data you used in your training is very important subject to push forward the current model to another level of using in practice. And this is another example where, for example, you train your segmentation algorithm on labeled data from an MRI sequence, and then you apply to CT. And then, of course, there are differences between the images, which might raise difficulty to deep learning or convolutional neural network models. And in this setting, this is what we call unsupervised domain adaptation, where you have training data for what we call source domain, for example, MRI images here. So you have, say, dozens, hundreds of 3D MRIs that are labeled pixel by pixel, but then you want to apply to CT and you don't have labels, you just have unlabeled data. So this is also a scenario of semi-supervision, but with also domain shifts. So you have labeled data in one source domain and unlabeled data in some target domain. And this specific problem is called unsupervised domain adaptation. So we want the model to use this unlabeled data here to generalize well on CT. So of course, if you just train your data on MRI, and then you try to apply to CT, you might observe significant drops in performances compared to just training on CT or using labeled data on CT. So you have bad generalization to the target, and this is one example, what you see here on the right-hand side. So, and of course, this is not domain adaptation or unsupervised domain adaptation is not just interesting in medical imaging because domain shifts are pretty much everywhere. Okay, so what you see here is an interesting examples of two different data sets of street scenes. One is generated by computer, GTA, I believe, and one is a real data set, cityscapes. And of course, if you train on one data set and you apply your trained model to another data set that is different, where the appearances of semantic classes might be different. For example, passes here in GTA look like training in cityscapes. Or if you go from one city to another, you train on 5,000 images in Zurich and then, or in Lyon, and then you apply to images of street scenes in Montreal during winter, then you might observe a significant drop in performances. So Domain shifts are everywhere, not just in medical imaging. It's a lot of interest in both computer vision and medical imaging, but we cannot label everywhere. So the trying to basically make model generalize better due to domain shifts is beyond just not having enough labels. It's about generalization, and we cannot label every single scenario that might occur. So these are examples, well-known examples also, where Cityscape is, for example, acquired in Zurich. So if you apply to a data, for example, acquired in Frankfurt or in Shanghai or in Montreal, you might observe a significant drop. And again, here, the effort to label data, for example, segmentation data in the Cityscape dataset on Zurich is huge, because you have 5,000 images and each takes 90 minutes at average. Okay, and then you have to do it again in every single city or in every new city, right? So this is why it is interesting to try to use unlabeled data and try to make the model generalize better. So unsupervised domain adaptation is also some form of semi-supervised learning, where you have unlabeled data in the source domain and unlabeled data in the target domain, and you try to make your model work well on the new target domain. So the difference basically between semi-supervised learning and unsupervised domain adaptation is just the domain shifts. Essentially. So in semi-supervised learning, we do not assume implicitly that we have different domains. So if you assume your images are lying in some 2D space, whereas in UDA, we assume that there is a domain shift. But the problem technically is essentially the same. Perhaps the difficulty is even worse with domain shifts. So, of course, weak supervision, all these are forms of weak supervision. Essentially, it attracts a lot of interests, probably hundreds of papers in computer vision. It's a little bit less in medical imaging, although we are seeing also many papers appearing in the major medical imaging publications like MICCAI, TMI, or media. So it's catching up. And I don't think to convince you about the interest of this, basically. So now, how we try to help in this, or how we try to solve in this, and technically and algorithmically. So what are the main models? What could we do, basically, with this? So one could not expect just magic. So we have to do something. And essentially, what is semi or weak supervision models doing, in a nutshell, is basically we try to take advantage of the data that is unlabeled. So we have data that is unlabeled. And how you take advantage of this data that is unlabeled is basically with prior knowledge about either your data or about the knowledge that you have about your problem. And in medical imaging, we have a lot of knowledge. For example, anatomical knowledge. And essentially, this is in some sense mimic also human perception, because I personally do not believe that we are just data-driven machines as a human. We have a lot of prior knowledge that we use about the world to recognize scene in the world. So this is essentially the motivation of it. So in the first part, which I will take care of in the remaining maybe 20 minutes or 15 minutes, I will talk about two general models for regularization. So these are some kind of structure-driven prior. So we make assumptions about the structure of your data, of your unlabeled data. And in the second part, Jose will talk about knowledge and data-driven prior. An example of knowledge-based prior for medical imaging is anatomical knowledge. If you have knowledge about the shape of the target organ or about anatomy, then you could use it to try to design unsupervised loss functions that will take advantage of your unlabeled data. So that's essentially what semi and weak supervision methods do technically. So let me go with part one. So I don't have time to go into a lot of technical details, but I will just, give the general concepts of what type of loss functions one could use and define over unlabeled data and why it's useful. So I will show you a very specific example that shows you how this is quite useful indeed. So the first example is something called, so it has origins in the area of Markov random fields and conditional random fields, which is very famous in computer vision and actually in shallow computer vision or in classical computer vision. So these type of regularization are very well known, and they are also known in classical semi-supervised learning, even beyond deep learning. So this is very simple intuition about it. Suppose that you just have a few labeled points and two classes. So you have the blue and green labeled points. So if you don't have unlabeled data, like what you see here, these points with the discontinuous lines, then you could have this decision boundary for your classifier, for instance. But then when you have unlabeled data, then perhaps it can give you some information about where the actual decision boundary of your classifier lie. So you will take advantage of the structure of your unlabeled data. And then one prior that's about the structure that come in head very quickly is that you don't want your classifier to cross dense region, for example, like this, in your unlabeled data. So you want your classifier boundary to cross just sparse regions in your data. So it is informative. Unlabeled data is actually informative. So this is a very general form. Let me introduce the notation very quickly. So essentially assume that theta is the parameter of your deep network, and f theta p is, for example, your predictions, your probabilities at the output of the network or some embedding, and yp are your ground truth labels. So you have a term that is very similar to full supervision term for the labeled data points. And then you have an additional term. This is a very general form of semi-supervision, which basically could have a very intuitive meaning. So I'll take a very soon I will take a very specific example. But this type of terms which depends on pairs of points, okay, both labeled and unlabeled, is essentially trying to make the decision boundary away from dense regions. So let's try to just make sure we understand the notation. So assume that you have a deep network, you have softmax output here. So these are the probability of whether a point belongs to one class or another. Let's say we have just two classes or segmentation into two regions. Okay, YP are the labels, and you have some potential WPQ that is some kind of pairwise potential between pairs of points. Okay, so let's say, for instance, I will try to enforce this prior or this unsupervised loss function. So what I'm telling my model here is basically if two points are close, okay, in the feature space or in some space or have some similarity, let's say WPQ evaluates some similarity between my points, then I want the prediction to be the same. I want you to pay high penalty if their prediction is different. Okay, so this is basically translating this information. Let's say 2 points are very close here. I don't want a decision boundary that go and separate them into the two different classes. This is exactly what this loss term is saying. So it's useful. It's basically prefer boundaries like this over boundaries like this. So let's take a very, so of course this is very common in semi-supervised learning, even before the deep learning area. The concepts are used in semi-supervised learning a long time ago. So let's take a very specific example here. So this is an example where you have, it's a standard semi-supervised learning example where you have basically a few pixels that are labeled and the rest of the pixels that are not labeled. So we have standard, for example, cross entropy term on the labeled pixels. And what we are telling the algorithm here basically is, okay, So here's the information. We are building similarity between pixels depending on their color, essentially, and we are giving some kind of perceptual prior to the algorithm. We are telling the algorithm, okay, pixels that have similar color, try to give them the same prediction. Even though we don't have the labels of these pixels, we are trying to put pixels with similar color together. And pixels that have different colors and are neighbor, they are very likely also to be edges. So we are encoding this information, this unsupervised information into this term, basically. And this is highly related to the Potts model in conditional random fields, which is very famous in computer vision, in classical computer vision, not deep learning computer vision. So a loss function like this will help you also take advantage of the unlabeled pixels. Okay? And embedding will help you embed prior on the fact that pixels of similar color, they are very likely to be in the same class. So, and this shows you actually the value of this. So I won't be able to discuss a lot of details, but essentially, if you just use a partial cross entropy, if you look at this point here, just basically a supervised loss on the labeled pixels, you are at this prediction, at this accuracy level, pretty much 50% Meow coefficient. And if you just add this term, this prior, it make you jump up to perhaps 53%. And this is just the number of labeled pixels on the scribble length. So essentially, you could get even close to full supervision pretty much with this type of unsupervised loss. This gives you some visual examples here. So an exciting part of this is that this type of unsupervised loss basically gets you 97% of full supervision performance with only 3% of labeled pixels. So the fraction of labeled pixels here is just 3%. So this is interesting. You could do things with unlabeled data. And here, essentially, we are imposing perceptual prior. We are telling the model, okay, put pixels that have similar color together, and pixels, that are neighbors but have completely different colors should be on the edges. This is what basically the information that we are feeding the model on unlabeled pixels. Okay, and of course, conditional random field losses are quite used also recently in medical images. So there are a lot of applications of this. So of course, I cannot go into the aspects of optimization. They are interesting by themselves in the context of deep networks. So I invite you to look maybe on some related papers. The references are here, but essentially this is quite useful. So let me finish with another example of regularization, which is a bit different. So what you could do also is, again, these terms are defined over unlabeled pixels. So what you could do is some kind of entropy, Shannon entropy. Here again, these are the softmax predictions for your deep networks. So look at the term, the supervised term here. So you have the label, YPC, log of softmax. And here, basically, you replace the label by a softmax, which is your prediction. So you don't have labels here. So intuitively, this mimics, the Shannon entropy term mimics a little bit the fully supervised loss term, except the labels are replaced by the softmax prediction themselves. This is also, again, is very well known in classical machine learning, in clustering also, or in unsupervised learning, and it's called entropy minimization. So essentially, what does this term do? It makes the prediction confident at unlabeled points. It's minimized here, okay? So it makes the prediction goes to 0 or 1 when you have two classes. And essentially also it tries to basically avoid that the decision boundary between different classes cross also dense region. So here is a visual example so that you see the value of this. So this is, here you have an unsupervised domain adaptation setting where you basically trained on some data and then applied on new data. So this is without entropy regularization. And this is with entropy regularization. So you could see that it pretty much makes the prediction within different classes quite crisp, quite confident. So they go to either 0 or 1. So they go to the vertices of the simplex. So this is by adding some type of entropy minimization, this type of term. And this is quite useful also in both semi-supervised learning and domain adaptation. Here is another medical imaging example where you can see the source data, and then you can see here the source entropy, which is good because your data was trained on the source data. But then you see the target output, where you have the performance dropping significantly, and also the target entropy. So this motivate why trying to minimize the target entropy would be helpful in a sense, so that you could have something similar to the prediction on the source, for instance. And of course, if you add a term for entropy minimization, you kind of observe a better performance on the target. This is an example again. So these type of regularization, even though they are simple and they are classic, also there is nothing completely new about these regularizations. They were used before a long time ago in clustering, in computer vision, in machine learning, but they are extremely useful to define loss functions based on the prediction of a deep network and to leverage unlabeled data, essentially. So let me take the last 3 or 4 minutes maybe to just give you an intuition why entropy minimization is good. In fact, assume your data is like this. So you have 2 classes. And your learning representation that is kind of entangled between the 2 classes. So this is high entropy and this is low entropy. So the entropy minimization pretty much prefer representations that disentangle your classes or that gives you high confidence. This is another example, for instance. So this is high entropy and this is low entropy. Of course, I don't have much time to go into the details how to generate these examples, but of course you could find this information in the references that are listed in the slides. So of course entropy minimization has to be used very carefully because alone it will just give you a trivial solution. It will go just to in this 2 class example, it will just go to 0 and 1. It has a gradient that is 0 also here. Okay. So that typically it should be added with other cues, such as the supervised learning terms, for instance, and so on and so forth. Okay. One way also to avoid trivial solutions is also to add other regularizations, for example, that ensure that the predictions are balanced between the different classes. For example, if you consider the specific example and then you have the prediction of class 1, which is the softmax output of the network, prediction of class 2, then of course, if you minimize entropy, there are bad solutions for which the entropy is minimal, like, all are put in the same class. Essentially. So what you can do is to use, for example, the marginal probability of labels or class proportion, which is basically the sum of softmax predictions proportional to the sum of softmax prediction over all points, and try to actually maximize the entropy of these label marginals. So the maximum is reached when all the classes have pretty much the same number of points. So this avoids the trivial solution of entropy minimizations, for example. This is one specific example. And it's interesting to notice that this is actually both the entropy of the predictions and the entropy of the label marginal or the proportions of the classes combined together. They give you the mutual information between the predictions of a deep networks and the labels. Okay, and this is also a well-known fact, for example, in clustering. Okay, in clustering, maximizing the mutual information is quite well known. We could also think about this as a combination between minimizing the entropy for confident predictions and also KL divergence between the label marginals and uniform distribution. So I'll stop here. Jose later will talk about specific cases, for example, or choices of these priors that could be used in conjunction with entropy. And we'll talk also about constraints like anatomical constraints, for instance, and so on and so forth. But what I want to mention here, and then we provide few references here, you could also find the detailed references in the slides. Essentially, and this is an interesting fact, I will just finish the next minute with this. So this mutual information, essentially the entropy plus the entropy of label marginals, is represent quite the state of the art in various settings of weak supervision, such as semi-supervised learning, few-shot learning, deep clustering, unsupervised representation learning, and unsupervised domain adaptation, essentially. So even though these regularizers seem simple, and even though the literature in all those areas of weakly supervised learning is quite huge today, both in learning, vision, and medical imaging, yet it seems that these type of regularizers, such as entropy, Laplacian regularization, or Markov random field regularization, and label marginal priors, or the mutual information, they seem to yield state-of-the-art performances in those area. So it's almost SOTA everywhere, and not exactly the mutual information itself, but parts of it, proxy of it, generalizations of it. Jose will talk about more examples that are more specific to medical imaging later. That's it, folks, and I hope you enjoyed it. It was a bit quick, but it will give you a little bit an overview about regularizers for semi-supervised learning, and hopefully the next year or the coming years, we will have a chance to talk in person. So enjoy the rest of the summer school, and I will leave the rest of this talk to Jose. Thank you.